Hello everyone. Today let's solve the problem number 104, maximum depth of a binary tree. So you can just go through the question and you can try to understand the question with the help of example that they have provided. So I'll just summarize the question so that it will be easier to understand, right? So what the question states here. What the question states here, we are given the root of the binary tree and we need to determine its maximum depth. So what is maximum depth here? Maximum depth of a binary tree is the number of nodes along the longest path from the root node to the farthest leaf node. Again, I'm telling this is important. This is what we have to find out, right? So the maximum depth of a binary tree is the number of nodes along the longest path from the root node to the, this is important, from the root node to the farthest leaf node. So this is what the maximum depth is. So let's come to the example here. What they have given, root 3, 9, 23, this one, 9, 20. Just give me a second here. So yeah, you can clearly see here 3, 9, 20, and then they have considered null because here we don't have anything over here, right? So they have considered null here, null, 15 and 7. So here what would be the approach here? So how can we solve this one basically? Let's see the same thing here. So first what we will do, if the root is null, this one, root node, if the root itself is null, will not be having the children at all, will not be having children and subchildren at all, right? So if the root is null, we can just return 0 in this case, right? So if this one, then next case is the depth of the tree is given by 1 plus maximum depth of left subtree and right subtree. Nothing but maximum depth of this one, maximum depth of left subtree and right subtree. We'll be calculating the recursion. This will be the recursive approach, right? This is because at each node, the maximum depth depends on whether the left or the right subtree is deeper, whether left subtree is deeper or whether right subtree is deeper. In this case, this is by one more thing, very important thing is here, binary indexing or indexing of the binary tree starts from 0. Just keep this one in mind. So this will be 0, 1. This one will not consider here. This is null, right? Here this is 1. Depth, right? This one, depth of the left subtree. Here, if we are considering the right side, it will be 3, 20, and this one, right? 15 or 7. It will be 0 here. This one will be 0, 1, 2. We can either consider 15 or 7. Same goes with both, right? 0, 1, 2. This will be 1 and 2. So we can just go with the maximum of left or right subtree. So the output will be here 2, right? So we need the solution as 1 indexed. We don't need the solution in 0 indexed. So we will add plus 1, right? Plus 1 to the whole. So it will be now 3. That is the reason we are going with the formula 1 plus max depth of left subtree and the right subtree, right? This is the approach that we'll be going with. Next, what we'll do, let's consider all the edge cases. Let's see all the edge cases one by one, and then let's write the code and discuss the complexities of the code that we have written. So let's discuss the edge case one by one. First edge case, let's go with the empty tree. When I say empty tree, so I'll consider input root equals null. So the output will be obviously 0, right? So when the value of the root is null, the output that we need to get here is 0. This is for the condition empty tree. So I'll just give here empty tree. So let's move on with the second edge case here. Second edge case, let's go with a single node tree. So when I say single node, I'll just consider here, let me consider 5 here, any number. So I'll just give here, we have to consider only one node here. So output will be 1 here. So the depth will, it consists of only root. If there is only one node or it consists of only root node, then the depth is quite obviously 1. This is for the condition single node tree. So yeah, this is the second edge case. Let's move on with the third edge case. So third edge case, let's consider tree with only left subtree. So when I say tree with only left subtree, I'll just consider here 1, 2, null, 3. So this will be in this way, right? This will be root. This will be 2. When I say null, we don't have to consider this one. And this one will be 3 here. Right? Tree with only left subtree. The output will be, the depth will be here 0, 1, 2, plus 1. The formula, we know that plus 1 of max of right subtree or the left subtree, right? So the maximum of the right subtree or the left subtree plus 1 we are considering. So this will be 3 here. So output will be here 3. So this is for the third edge case. Let's move on with the final edge case or the fourth edge case. Nothing but tree with only right subtree. Here I'll just consider the input root equals 1 comma null, 2 comma null, comma 3 here. This will be 1, 2, 3. Right? This is fine. The depth is again here similar to the last one. It will be 0, 1, 2 plus 1 we are doing. So the output will be 3 here. In this case, output will be 3. The depth will be 3. Right? So this is for the condition tree with only right subtree. With only right subtree. So these are the 4 edge cases that we need to consider. First one is empty tree. Second one is for the single node tree. Third one is for the what we consider tree with only left subtree, right? So I didn't write here. This is fine. Tree with only left subtree. This is fine. And the final one was for the tree with only right subtree. I hope all the edge cases are clear. And one more thing, as I have said, this is important. Binary tree indexing or the indexing of the binary tree starts from 0. That you have to keep in mind. So this is it for the edge cases. Next, let's write the code and I'll explain the code once we write the code itself. And then finally, we will be discussing about the complexities of the code that we have written. So let's start writing the code. So I'll just remove this one. We can just write the code in single line. This is simple code basically. So I'll just consider here where max depth equals, let's pass the parameter root here. This was there. And we know if root is present, then only if tree is empty or if root is null, we have to return 0. As there is no depth at all. We have discussed about this one. So otherwise, we'll calculate the depth recursively. If root is present, root node is present, and then we have the further, children and the sub-children, then we'll be calculating the depth recursively, right? So we have already discussed the formula is 1 plus maximum of left subtree depth and right subtree depth. So I'll just give here 1 plus max. We can just consider here math.max. So just give me a second here. This is fine. Math.max of max step. We're going with the recursion, right? Recursive function here. Max depth of 2 dot left. This is fine. And again, right side also we have to consider. I'll just give here root dot right. So this is it. Else we have to give 0. If the root itself is null, then we have to give 0, right? So else I'm giving 0 here. This is it. Let me format this one once and let me hit the run. So you can clearly see the sample test cases are getting passed. So let me hit the submit now. So you can clearly see all the test cases are getting passed here. So the code works absolutely correct. So let's quickly discuss the time complexity and the space complexity of the code that we have written. So the approach that we went with here is a recursion or the recursive DFS, right? We know this. And the overall time complexity would be here big O of n. Why the time complexity here is big O of n? Because we are visiting every node once. You can clearly see we are visiting every node once, right? So that is the reason the overall time complexity would be big O of n. So what will be the space complexity here? The overall space complexity would be big O of h. Why the overall time complexity would be big O of h here? Because it mainly depends on the tree height, right? So it can be big O of log n for the balanced trees, or it can be big O of n for the skewed trees. So overall space complexity we can consider in this case big O of h. I'll just give here space complexity would be big O of h. So I hope the solution is completely clear. For now, this is it. Thanks for watching, guys.